Okay, function notation. Um, what function notation is, well, it's simpler to just do a few examples. So let's say you had several functions. Let's say you had y, or no, I'm using the word function, but let's say you had several equations, like two variable equations, like y equals 2x plus 1. And maybe you had y equals 3x squared minus 4x or something like that for a rule. And we needed to distinguish between the two. Well, it's really hard because they're both called the rules. Like here's the rule 2x plus 1, and here's the rule 3x squared minus 4x. Our problem is we don't know how to distinguish between these two y's. So maybe I want it plugged into the bottom one. Well, there's got to be a better way to do that. And so what what mathematicians have come up with is what's called function notation, where we use a symbol like this, f at the value of x. Like I say, the function f at the value of x. And then that's gonna be what represents y. And it doesn't have to be f, it could be anything. If you're dealing with money, maybe you'll call it m at x. So maybe it looks like this. So the money you make at the value of x is the same as also saying y. It's just another way to name functions. So instead of y equals 2x plus 1 and y equals 3x minus 3x squared minus 4x, I'm gonna call the top one f at x, and I'm gonna call the bottom one p at x. So now, when I say I want to know the value of x in the function x when x is maybe 2, so so I might say something like this. I want the value of f when x is 2. So all you do is take the 2 and plug it in for x here. So 2 times 2 plus 1. So that'd be 5. So that's just generally function notation. You could also, sorry, I'm going to make this move a little bit. You could also then ask for maybe p at negative 3. And so that would be 3 times negative 3 squared minus 4 times negative 3. And that's just a matter of this is telling you what to plug in to the p rule. And so you would have 3 times 3 is 9, so that's positive 9 times 3 is 27 here, plus 12 because we got two negatives. And so we know p at negative 3 is equal to, looks like 39. Yeah. And so that's essentially all function notation is. It's just a way of naming the rules so you can keep track of them. What rule we're dealing with at the time. Because in a problem, you might have, well, you could have 100 different equations, but most of the time you're going to have in an algebra class, you're going to have one or two or three equations in one problem. So let me pause for a second and catch my bearings and show you the next part of function notation. So here's a situation um, that might maybe bring it to some light. It says Hogan's parking lot charges a flat rate of $5 per day to park in their lot. Jack's parking lot charges $2 to enter the lot and $3 for every day it is left parked in their lot. So you got these two parking lots, and they have a little different pricing schemes. So, if you wrote a function for Hogan's, I might call it h. I might let h stand for, why use capital H? We'll use lowercase h. Not that it matters. So h will let represent the total cost of parking. I want to say money all the time, but total cost of parking in their lot. And for Jack's, we'll call that maybe J. J is the total cost of parking in their lot, in Jack's lot. And this is total cost of parking in Hogan's lot. All right. And we're not worried about possessive. I didn't put my marks correctly for Jackson, my possessive apostrophe. Well. But anyway, so the cost of parking, and I'm going to let D represent the number of days parked in the lot. So if you were needing to probably leave your, not that it matters which plan you pick, but if you're needing to park your vehicle there for several days, you'd probably pick Jack's, and if you're, had to go get your car every day, you'd probably pick Hogan's. And it really doesn't matter in that case. But still, here's what the function will look like, because that's really what I want, is the function notation. So the rule for parking in Hogan's lot might look something like this. H at the value of D equals $5 per day. That's pretty easy. And then Jack's rule might look something like this. J at D is equal to $2 per day plus the $3 entry fee. So now you could find, you might ask then, what does it cost if you park in Jack's for 10 days? Well, that would be 2 times 10 plus 3. Or maybe you want to know what Hogan's rule is for 10 days. So this leaves no question that we're talking at which rule we're talking about. Whoops, not D, sorry. So we were doing 10. So 5 times 10 plus 3. And so Jack, the cost of Jack's at 10 will be $23 after 10 days. And Hogan's, see, and I have it wrong, sorry. Hogan's would just be that flat rate of 5D, so 5 times 10. Nothing to write it down wrong to confuse you. But 5 times 10 gives you $50. So quite a bit cheaper. That would be evidently if you left it in their lot for 10 whole days. But if you had to go get your vehicle every day, at Hogan's it'd be $50. At Jack's it'd be $23. And so that's one way of showing how you can tell two rules apart. We had two specific rules in this problem. We named them both separately. So just on a final note, and I'll stop. So let's give two more examples. Let's say I had, we've used lots of different letters. Let's say Z at X equals maybe the absolute value of X plus 5 over 3 is one rule, and maybe J at X now is equal to 6x squared plus 2. Just making up a couple rules. So we've got two separate rules, and so we name them, we give them different names. We call the top one the Z rule, bottom one J rule. Again, this function notation is just naming things so that we can keep track of them. So Z, maybe I want Z at the value of -6. Okay, well, Z at the value of -6. So this tells me to go to the Z function and plug in -6 wherever there's an X. So -6 plus 5 divided by 3. Well, -6 plus 5 is -1. Absolute value of that is +1. And so it would be 1/3. Right? Or maybe I want to know J at -2. Okay? So if you want to know the what -2 would be plugged into the J rule, that would be 6 times -2 squared plus 2. And notice I put parentheses around this -2. Get in the habit of doing that, because if you type in, just as a side note, If you just type in 6 times negative 2 squared plus 2 in your calculator, it will do that problem incorrectly for you because it won't square the negative. You've got to have parentheses in that thing, especially with the new calculators we have. Just notice that today on about 20 different kids' papers. So when you do this problem, then you can do the order of operations. So 6 times 4 plus 2, so 24 plus 2 would give you 26, would be the value of the J rule at negative 2. And you don't always need, and this will be my last example, you don't always need numbers. You could find the J rule at the value of a plus 1. Okay, wow, now that's getting kind of freaky. But what it is you're just plugging that, it's telling you to go to the J rule and plug in a plus 1 wherever there's an x. So let's do that. 6 times a, wow, 6 times a plus 1 squared plus 2. And so now you could do, the fancy rules to simplify this, but essentially you're done. Now if you want to simplify it, it might look something like this, because you've got to go ahead and a plus 1 squared is a binomial. You got to write it out twice. Now you're going to have to FOIL it. So you'd have 6 times, and I'm not, I'm doing first, outer, inner, last. Some of you might know it as FOIL. I know it as distribution. And so you just have a squared plus 2a plus 1 if you do all that, and then plus 2. And if you kept simplifying, now you can distribute the 6 through, so 6a squared plus 12a plus 6 plus 2. And so that would be J at the value of a plus 1. And so that's function notation, and you can take it a lot further than that, but this is just your introductory video into it. So hopefully it helps. I've taught this in many, many different ways, and hopefully this one works for you. So best of luck, and comment if you have a question.